Hello and very good morning to everyone. My name is Thrissha Devanderan. My matrix number is 217120. Today I'm going to explain to you about the first and second law of thermodynamics. This is an assignment for EMM 3316 thermodynamics class. Thank you. So before going into further details about what is the first law and what is the second law, what is the application and more, we should understand what is thermodynamics. So thermodynamics is a physics branch on how heat, work, and temperature relates to energy, radiation, and the fundamental properties of matter. Thermodynamics specifically discuss how thermal energy is changed into or out or other type of energies and how it process affects matters. The energy that heat produces is known as thermal energy. The movement of small particles heights an object causes heat to be produced, and the faster these particles move, the more heat is produced. Then, the manner and speed of these energies exchanges an unimportant in terms of thermodynamics. It is based on the starting and ending of the transformation. Thermodynamics is a macroscopic science, which is like a very big scaled and large scaled. This indicates that it works with the bulk system rather than the way matter is made up of molecules. It doesn't really focuses on the tiny bit of particles, but also rather it focuses on how the bulk system actually works. We should understand the basic concept of thermodynamics. These slides shows you the relation from a very outer and third person perspective so that you could easily understand it. So for thermodynamics we have three important factors. It's not really a factor which is causing something, it's just a tiny bit of properties, which is first system boundary. It may be real or imaginary, fixed or deformable. For example, you can see this picture which looks like a cell. Where is our system boundary is, which is the one with all the lines. Then the surrounding. Surrounding is everything outside of the system that has direct influence on the behavior of the system. It can be anything of that system, maybe temperature, heat, outside work, anything. Then the system, which is really important for us. A thermodynamic system is a specific portion of matter with a definite boundary on which our attention is focused. So from here we can see that the surrounding and the system usually correlates heat and work in terms of any properties like heating system, cooling system, spindles, pistons, anything. It just correlates its work and heat. Okay, so we already see what a system is, what a surrounding is, what a work boundary is. So now we should go into detail about what are the thermodynamic processes. When a system undergoes an energetic change that corresponds to a difference in pressure, volume, temperature, internal energy, that's when the thermodynamic process actually starts. So there are four different type of processes which we majorly sees or discovers or go further into detail. First is adiabatic process, a process which where no heat transfer into or out of the system. This means the Q will remain zero. Next, isochoric process. This is when a process where no change in volume occurs and the system does not do any work. Next, isobaric process. Isobaric process is a process where there is no change in pressure. Next, lastly is isothermal process. Isothermal process is when there is no change in temperature. There is no movement of heat going from high to low. This is four different types of processes which we should focus. As in for thermal, there's a property of temperature. As in for mass, there's a property of concentration. And just like that, as in for thermodynamics, it has its own properties where we use to calculate, quantify things. A definition of thermodynamic property is characteristic elements of a system able to describe the state of the system. Both extensive property, which is dependent on the mass of the system, and the intensive property, which is independent of the system, are thermodynamic characteristics that are attainable. Two major properties, which is enthalpy and entropy. Entropy will be focused in the second law, and enthalpy will be focused overall as a major. Enthalpy is the measurement of energy in a thermodynamic system. A system's enthalpy value is its overall heat content, which is also equals to the internal energy plus the sum of the volume and pressure. Next, entropy is the value which depends on the physical state or circumstance of a system. In other terms, it is a thermodynamics function that is used to quantify disorder or randomness. So now we will go to the exciting part where we talk about the laws of thermodynamics. Thermodynamic system at thermal equilibrium are characterized by fundamental properties of variables, which is energy, temperature, entropy, internal energy, and more. These laws of thermodynamics govern how these quantities function in numerous circumstances, where we talk about how entropy affects the system, how temperature, how energy, how the internal energy enthalpy will affect this system. So let's go on the first law of thermodynamics. What is first law of thermodynamics? According to the first law of thermodynamics, heat is an aspect of energy, and as a result, thermodynamic processes are governed by the idea of energy conservation, where it doesn't really changes. Heat energy cannot be created nor destroyed. Hence, this means it can be moved from one place to another or changed into out or in of different kinds of energy, where thermal energy changed to kinetic energy changed to potential energy, and many more. Major equation of this law is Q equals to U plus V. Q is the change in heat, U is the change in internal energy, and W is the work done on the system. The quantity Q minus W is therefore independent of the root and combined by to modify the state, as shown by the equation as I stated above. Also, we can state that the internal energy rises when a system receives heat or vice versa. This law implies that some heat applied to the system is utilized to change the internal energy, while the remaining heat is used by the system to transfer work in and out. So we can see how Q, U, and W correlates to each other in this law. As I stated earlier about W, which will be equals to Q minus W is U. W is the work done, which can also equals to negative P delta V. P will be the external pressure of the system, and delta V is the change in volume. This is specifically called pressure volume work. A system would have less internal energy if it produced heat and or operated. As a result, when a system's heat is increasing, which will be accomplished by adding heat to the system, its internal energy will also increase. If a system were to receive work, it will also require more internal energy. The energy within the system is altered by any work or heat that enters or exits into the system. The first law of thermodynamics states that the energy can never be created or destroyed. Hence, the change in internal energy is always equals to zero. In the event that the system is losing energy, the environment absorbs it. When the energy is taken up by a system, the environment releases its energy. As you can see, delta U system will be delta U equals to surrounding. U is the internal energy. There are few processes and signs which we should forever remember, as seen for first of thermodynamics, where work done on the system will be negative and work done out of the system will be positive, as and vice versa. Heat given to the system will be positive, and heat absorbs out of the system will be negative. As I stated earlier, the effects of different surroundings and changes on a system help determine the increase or decrease of internal energy, heat, and work. As I stated earlier, the four different processes in thermodynamics, which is adiabatic, isobaric, isochoric, isothermal. These four processes helps us to determine how the internal energy, work, and heat correlates and alters the system, which can be seen in this table. This is simply an example of first law, which is the first law in closed system. It is moving with respect to a reference lab, where Z is the elevation of the center of mass above the reference plate and V is the center of mass gravity. We can see that how the works and heats going in and out of a system and how its elevation is altering it. The first law of these processes expressed as the total energy entering minus the total energy leaving is the change in the total energy of the system. E in minus E out is E system. E system can also be quantified as Q minus W. So lastly, it goes on from an equation of E in minus E out is equals to Q minus W. So the last few slides explains to us about what is thermodynamics, what are the properties, what are the process involved. So we would have a basic knowledge on what is the first law of thermodynamics. Now we will focus on what is the second law of thermodynamics. The direction of heat transmission and the achievable efficiency of heat engines are constrained by the second law of thermodynamics. The universe energy is constant according to the first law of thermodynamics. Although it can be exchanged between a system and an environment, energy could never be created or destroyed. If a process does not stick with the first and second law, I bet it could not take place. Let's see what is the second law of thermodynamics. Given the second law of thermodynamics, any naturally occurring process will cause the universe entropy. Entropy has a symbol of S to increase. The law simply stipulates that the entropy of an isolated system will never decrease over the time. However, there are some circumstances where the overall entropy of the system and its surroundings stays constant, such as when the system is in thermodynamic equilibrium or the a reversible process. The law of increased entropy is another name for second law of thermodynamics. The second law of thermodynamics established the standard for every process's feasibility. The second law of thermodynamic equation is delta S universe is always more than zero. Delta S universe is the change of entropy in a system. Entropy is an indication of the system's randomness or the amount of energy and chaos present in a individual system. It can be seen as a numerical index that rates the energy's quality. The entropy of the closed system is increased for a number of reasons. First, the heat is exchanged with the environment in an enclosed structure where the mass stays constant. The system becomes disturbed due to its shift or in heat constant content, which raises the system's entropy, which is the randomness of a system. Secondly, the basic modification to the system's molecule movement patterns may take place. This results in disruptions which further causes the irreversibilities inside the system, which will be increasing the entropy. Now let's look about the statement of laws. The second law of thermodynamics is stated in two ways, which is Kelvin-Planck statement and also Clausius statement. Kelvin-Planck statement says it is impossible to create a device that operates on a cycle and extracts heat from a single reservoir to produce work without any other effects. Then it also states that, put more simply, it means that no machine such as an engine can be created that can be utilized all of the heat generated by a single source and still have heat left over. When heat is converted into a work in a cycle process, some waste or leftovers of heat is inevitable. Then, Clausius statement. To put more simply, it means that the natural flows from a hotter to a colder object in a closed system and does not flow in any other direction unless the system is subjected to external forces or undergoes work. This assertion highlights that the directionality of heat transfer, emphasizing that heat does not spontaneously transfer from a colder to a hotter body. To be put in a more simpler and shorter way, heat cannot flow spontaneously from a colder body to a hotter body without any application of external work, such as piston, spindle, shaft work, more. If it comes to the entropy, you should straight away strike about Gibbs free energy. What is Gibbs free energy? Delta S total is equals to delta S universe, which is also equals to the surrounding and the system. As in I've said earlier, surrounding is everything else other than system which affects directly the system. This formula for entropy is the change in the surrounding, where the surrounding is equals to the enthalpy of the system, the change of enthalpy of a system divided by the change of time. If this equation is replaced in the previous formula, it will be changed as delta T delta S universe is equals to delta H of a system minus T delta system delta entropy system. If the left side of the equation is replaced by G, which is known as a Gibbs free energy, it will directly change to delta G equals to delta H minus T delta S. This is the Gibbs free energies equation. Delta H refers to the heat change for a reaction. If a positive delta H means that heat is taken from the environment, endothermic process, and if there's a negative, it means exothermic, where heat is transmitted or emitted. Delta G means the change of a system's free energy in which a reaction takes place at a constant temperature and pressure. We could use the last few equations to check whether our system is spontaneous or non-spontaneous in numerous situations. First, the equation states that regardless of the system's temperature, the free energy change is positive and non-spontaneous when entropy is falling and enthalpy is rising. And when both entropy and enthalpy increases or decreases, temperature becomes relevant. Thirdly, when entropy and enthalpy are both positive and the temperature is low, this reaction is not spontaneous. Conversely, when both are positive and the temperature is high, this reaction is spontaneous. Fourth, when both enthalpy and entropy is negative at a low temperature, the reactions are spontaneous, and when both are negative at a very high temperature, it become the reactions are not spontaneous. Since entropy is increased by all spontaneous reaction, it is possible to ascertain whether the entropy varies depending on the spontaneous nature of the reaction. To give us a more clearer view on what I just explained in the previous slide, we can use this table to use delta H, delta S, and delta G to determine the property of a system, whether the reaction occurring is spontaneous or non-spontaneous in various other temperature effects. For example, when delta H is negative, delta S is positive, the Gibbs free energy change will be negative. Thus, the reaction is spontaneous at all temperature. This is how you should read the system based on the previous equation and also the previous explanation of the slide. So those are all about the second law of thermodynamics, and we have seen a tiny bits of first law and second law. Now we can come to a conclusion, and I hope you really have a basic knowledge on what and how the first law and second law actually works. In summary, the conservation of energy principle is established by the first law of thermodynamics, which emphasizes that energy within a system stays constant despite its ability to change forms or transfer between a system. You should always remember energy could never be created or destroyed but can be changed from one form to the other. The second law of thermodynamics, on the other hand, clarifies that the directionality of process by demonstrating how natural processes occurs eventually tend towards greater entropy or disorder. Taken collectively, these laws serves as the fundamental basics for comprehending conservation, energy transformation, and the innate constraint and inclination of this cosmos. Understanding and putting this law to use help us understand how energy and system behave, which helps us innovate and engineer and make wise decisions while taking thermodynamic basic limitation and opportunities into account.